This class is mathematics heavy, and we're going to review a few important areas, but it's no replacement for a rigorous class in the material. But I'll try and just mention things that we'll see a lot in this course. Henry Poincaré wrote that later generations will regard set theory as a disease from which one is recovered. John von Neumann, who I love this writing, wrote, "The emphasis on mathematical methods seems to be shifted more towards combinatorics and set theory, and away from the algorithm of differential equations, which dominates mathematical physics." I think this is a lesson for young mathematicians, physicists, and engineers. Let's look at some set theory. First of all, there's universal qualifiers, or the for all symbol, and this symbol means that a statement applies to every element in a set. For example, if we say for all x in a set, we mean that whatever property we are discussing holds true for every single x in that set. There exists, or as the existential qualifier, this means that there's at least one element in a set for which a statement is true. For instance, there exists an x in a set means that there's at least one x in that set which has the property we're describing. A union of two sets includes elements that are in either particular set. And if we combine all the elements from two groups into one big group, the intersection symbol will mean that two sets includes only the elements that are in both sets. And we might think of this as common items shared between two particular groups or sets. A subset, for example, a set A is a subset of B if every element in A is also in B. This also means that A is entirely contained within B. A proper subset means, for instance, that a set A is a proper subset of B if A is a subset of B but A is not equal to B. So this means that A is some but not all the elements of B. The compositions of function symbol at the bottom means that when we might apply one function to the result of another function, we might have two particular functions f and g. And the composition means that you might apply g to an input and then apply f to the result of g. Subsets, for example, if we have two sets, A and B, then A is a subset of B if every element in A is also in B. So this would mean A is being a subset of B. And formally this would mean that for every element x in A, x is also in B. And if A is a subset of B but not equal to B, then we might call A a proper subset of B. The intersection of two sets, for example A and B, would include only those elements that are in both A and B formally. And this means that the set of elements are in A and B at the same time. There's also the union of sets we just mentioned. And if there's A and B, they would include all the elements that are in either A or B. This might mean that the set of elements that are in A or in B are indeed in both. When we have a collection of sets, the union of all sets includes all elements that are in at least one of the sets. A difference of sets means that if we have a sets A and B, those elements that are in A are not in B. This means that A has all of the elements of B removed. Symmetric differences of sets means that there might be two sets A and B, and they would include elements that are in either A or B, but not both. It's very much like taking the union of A and then removing the intersection. A complement. If we're given a universal set, the complement of set A includes all the elements in the set U that are not in A. This depends on the universal set U. It's like everything outside of A within the context of U. So, set theory is the foundational framework in which modern mathematics operates. And the set builder notation describes a set by specifying conditions that elements must satisfy. It's usually involved in a variable, a separator like a colon or vertical bar in the notation, and a particular condition. For example, the set of all x might contain certain conditions like true. For example, when we use set builder notation, we might write it as all X such that a specific condition holds true. We can also specify domain, meaning the set belongs to something, to define the set. Membership symbol, this is basically meaning that an element is a member of a particular set, and you'll see that a lot, the membership symbol. You might also see the logical and or operators, and these are pretty obvious, but like and would mean an indication that two conditions must be true. You often see this in programming, like in if statements where you might hit if and or. This is just basically a summary of our notation. And let's just look at some examples just to solidify the concepts. So 7, 3, 15, 31 might be a set with specific numbers, and it includes exactly only those 4 numbers. A set of positive real numbers includes all numbers greater than 0. A set of absolute value of 1 includes the numbers -1 and 1, which might also be defined as all numbers whose square is 1. A set of pair of real numbers where the second number is greater than 0 and less than a given particular function value. Or a set of even natural numbers includes all numbers that can be written as 2 times another natural number. The symbol for and means both conditions must be true, and the symbol for there exists perhaps means there's at least one number satisfying the condition. So set theory and classes in it are pretty straightforward and very logical, and it's probably worth the time before continuing to maybe just download some PDFs or look at some websites on the internet as you go along or have questions, get used to it. I think most people with math degrees today have studied set theory in classes, but it's very rare for engineers and maybe even physicists and other people in STEM outside of math to study it. And I'll try and focus more on the math and physics side of the equations, but it's important to just have this basic notation to understand the language of analysis of Navier-Stokes equations.